Hi, this video is mainly for the students in my fall 2017 analytical chemistry class to follow up on what we didn't finish in lecture. So if you're a regular YouTube video watcher, you might find this to be a little bit disjointed and you might not want to watch. I do have 3 other chromatography videos that have this information more in context. But for my fall 2017 class, who are looking for information for their quiz tomorrow, this is for you. So where we ended in class today was talking about resolution, and as I said in class, you want to have a resolution that is at least 1.5 so that you're able to have a good baseline separation between peaks. The resolution equations that you want to pay attention to, or you want to make sure that you're able to memorize this resolution equation of the difference in time, retention time, between the 2 peaks. It's important for you to realize resolution is between 2 things. You don't really have a resolution if you just have 1 peak. And that it can be based on the average width at the bottom, right? So the one that's got just the width average is for the bottom. And we also have the width at the half height. And the width at the half height is this equation right here, where you've got that scaling factor. Okay, so diffusion. As things go through the column, your analytes, your solutes, they pass through the column. You start with a very thin band, and over time this band will become broader, and that's mostly because of diffusion. You think about the fact that you have this high concentration of your analyte at the beginning, right? So there's your high concentration. And you know things diffuse from low concentration, or sorry, from high concentration to low concentration. So if you just let it sit alone with no flow, that bright blue, highly concentrated band is going to diffuse into the gray area. Same thing happens when there is flow. And so as you go over time, the peaks are going to get wider because of this diffusion. The standard deviation of the width of that band of analyte, the peak essentially, is equal to the square root of 2 times d, the diffusion coefficient, times time. So you're going to get a wider peak the more time goes on and the larger the diffusion coefficient. The diffusion coefficient, of course, matters. So here are some example diffusion coefficients. If I was looking at sugars, for example, sucrose in water, then I have a diffusion coefficient of 0.52 times 10 to the minus 9, and that is in units of meters squared per second, right? So you expect to have a wider peak for a larger diffusion coefficient just because it means that per unit of time, the area is expanding greater. Now, plate height is something that chromatographers use to describe the resolution and the lack of diffusion. And plate height is this fake artificial construct. You might hear some people talk about the number of theoretical plates. And a theoretical plate is like one distillation, essentially kind of similar to a distillation step. We talked in class about having the extraction between solvents, and the more times you extract a pair of solvents, the more you're going to get the analytes isolated. So in this case, the number of theoretical plates is how many times that happens, how much space, the distance it actually takes for a single separation event to occur. I'm using a lot of air quotes here because it's not actually working in steps. This is basically like how big is a store in the mall analogy. So it's the proportionality between variance, which is our standard deviation squared, and the distance traveled. And ultimately in the blue box down there, that's what you want. Plate height equals standard deviation, and that's the width of the peak, right? Standard deviation of the width of the peak. We're kind of going with this Gaussian distribution over x, and x is the distance traveled. So this depends on the flow rate. We've got the linear flow rate. You've got the x squared equals 2 dt. Remember, previously sigma was equal to the square root of 2 dt, so you just square both sides. That gives you sigma squared equals 2 dt. And you're like, well, the time that it took is how far it went divided by the flow rate, so that's cool. And we just define this thing of plate height being 2 times the diffusion coefficient divided by the flow rate, okay? And that means that now you've got that h, x equals sigma squared, and oh, cool. H is defined as 2 times d over mu x, 2 times the diffusion coefficient over the flow rate, but really we're saying this is standard deviation squared over the distance. Now, plate height, like I mentioned, is the height equivalent to a theoretical plate. It's approximately how long in the column you have to go for one equilibration cycle, where the solute is going between the mobile phase and the stationary phase. Mall analogy, how long distance it takes to go in and out of a store on average. And like I mentioned, it came from old-fashioned distillation terminology. What you need to know is that a smaller plate height, smaller h, means a smaller peak width, so smaller standard deviation, and that equates to better resolution. And better resolution is better separation between peaks, and the whole point of chromatography is separating peaks. So small plate height is good. Now the number of plates on a column, n, large N, really is simply, okay, n equals column length divided by h. So how many can you fit in there? Well, how much space do you have, and how big is the single plate? So we can use this of n equals column length divided by the plate height. And there's also a few other math derivations. I'm sure you don't care about the derivations, you're just interested in the result. But say that you can get the number of theoretical plates, this big N, based on a few things that you can measure off a chromatogram. It's really important to find stuff you can measure off a chromatogram. So it's based on the retention time. So this can be described for a single peak, right? And in fact, that's what these formulas are showing you, is you have the retention time, TR, squared, times 16, and you have the width squared. Now that width there is that baseline width at the very bottom. And then you have these scaling factors where if you decide instead that you want to use the width at half height, then you need, instead of a 16, you need the 5.55 there. So if you've got the retention time, you have the peak width, you can calculate the number of theoretical plates, which is cool. Now, you might have guessed that resolution is related to this, because if you have more theoretical plates, you have skinnier peaks, less diffusion, and better resolution. So here's that. Resolution is square root of n over 4 times gamma minus 1. And remember, gamma is that relative retention where it's the retention time of the second peak over retention time of the first peak. So that's the little white box over there. So if you're trying to use this formula, you have to make sure that you're calculating gamma and putting it in, okay? So you can increase the resolution of your chromatography experiment by increasing the number of theoretical plates. Easiest way to do this is to increase the length of the column. More length of the column equals more theoretical plates. If you doubled column length, then you're going to increase the resolution by the square root of 2. Because doubling column length doubles the number n of plates. You can also increase the resolution by increasing gamma, which is that unadjusted relative retention. Because that is telling you about the relative speed at which different analytes are going through your column, basically the relative likelihood that they're going to interact with the stationary phase, you can mess around with gamma by changing the stationary phase itself, how polar or nonpolar it is in HPLC, for example. And also you can change the mobile phase. And so that can really help you. If you've got a different interaction, a different partition coefficient between the analytes of interest, then you're able to change gamma. So you can always increase the number of plates by buying a longer column. By the way, you do have to buy a longer column, or you can change the stationary mobile phase composition. Now here's a graph illustrating how much better the resolution is when you have more plates. What they did is they cycled an analyte through a column over and over again. So it's actually going around. So they have a number of passes here. And it's 2 peaks, and you can see that for one pass through, you barely have any separation at all. So that's that data point right there. It's almost impossible to tell that there are 2 peaks. And then by the time you get to maybe 5 or 6 passes, which is about here, so oh look, 7 passes. Now they've labeled that these are phenanthroline and deuterated phenylalanine, excuse me. And then as you go on and on, more passes, better resolution. This is the equivalent of lengthening your column by passing it through the column multiple times. Now, plate height, you want a small plate height, so small is good. Plate height doesn't only depend on chemistry. So number of theoretical plates relates to resolution. You can change resolution with gamma, but it also depends on flow rate. And so the Van Deemter equation is a pretty famous chromatography equation, and it tells us how the column type and the flow rate affect the plate height. So the speed of the liquid or the speed of the gas going through the chromatography is your flow rate. And so h, your plate height, small is good here, is proportionally equal to, so nice little squiggle equal sign, 3 different terms. And one of those is the A term, multiple paths. B term is about longitudinal diffusion, that's that spread. And the C term is about equilibration time. And U sub x is our linear flow rate. And I will talk to you in just a moment about each of these. So let's do it. The Van Deemter equation gives you kind of what I like to call the Nike swoop, okay? Where what you're plotting is the plate height, h, versus the flow rate, u, x. And because the A term is a constant, you have this constant flat line, all right? Because the B term is divided by ux, it's something that starts nice and high. Well, not nice, you don't want it to be high. And it goes down, and as flow rate increases, that decreases. The C term is something that's proportional to flow rate, and so it actually increases with time, and that's this part up here. Now, all 3 of these combined come together to give you the actual plate height that you see. And so you have to add these things up. And so if I add this distance here to itself again, and then that again to there, then I'm building up that distance, and what, that distance in order to get that. Now, there's a sweet spot where you get the best plate height, which is your best resolution for a given flow rate. If you go too slow on the flow rate, you're up in this zone up here, which is bad. There's a nice frowny face for you. But if you go too fast, then you're also in this zone, which is more of a meh, right? Of course, where you want to be is you want to be right at that sweet spot where everything is lovely. So how do we understand these 3 terms? The A term is the multiple flow path term. In my mall analogy, I like to think of this as how many kiosks are in the aisle. Those malls that are full of those kiosks with the watches and all of that stuff are really hard to get through. And if you're literally just a solvent molecule flowing on by, you're going to have multiple paths you can take. And so here you have on the left-hand side of the figure, you have all 3 molecules in the same position as each other. And molecule 1 takes a pretty much direct path through and comes out first. And then the next molecule is a little bit more of a tortuous path. It's got more obstacles to avoid. It comes out later. And then molecule 3 eventually, after meandering around all of the obstacles, comes out later. And so the net effect of this is that by having multiple paths around the packed particles to take, you're going to have a broader peak. And this is a constant, just has to do with the packing of the column, has nothing to do with the time that you spend in the column, and therefore it doesn't have anything to do with the flow rate. So that's why A is a constant. It's just the variety of routes. Now, if you have no packing, which means you have an open tubular column, then the A term goes away. And it turns out in GC that you typically don't have a packed column. Now, some GC does, but most GC is open tubular and so has better resolution than LC, simply because of the fact that the A term is 0. You don't have multiple paths to go through. It's open. It's all direct through. Yay for you. The second term, the B term, is that longitudinal diffusion that I talked about. The more time that you spend in the column, the greater the diffusion will be. And so if you spend less time by going through at a faster flow rate, then that's great. So as you increase the flow rate, right? So here's our increased flow rate. Then you're dividing by the flow rate, and you're able to get less of this diffusion because you're simply not lingering in the column as long. Now the C term is the hardest one to describe. It is the equilibration time. So you have to remember that some of your solute stays in the mobile phase, even if it mostly prefers the stationary phase. So you and your friends all like shoes equally, and you're all as likely to go into a store. But if we start with you all going in here, so that's the starting point. Some of you are inside the store, some of you are outside. Remember, those of you in the hallway, in the mobile phase, are continuing to walk down the path because of the fact that everybody's going that way and they kind of push you along. And so even if you have an equal likelihood of going into the store, going onto the stationary phase, you're going to get this shift down here. So this is after some time. Pardon my handwriting. So after time. And so now you've got a broader peak because some of you have stayed in the store while others have moved on. Can you imagine if the mobile phase is going really fast? By the time you've gone in the store, looked around, and decided to come back out, your friends are already way down the hallway. Now, you and your friends, in my analogy, have the same chemical properties, and so you're the same analyte here, and so the peak has really spread out. So the faster the mobile phase moves, the higher the flow rate is, the worse this phenomenon gets, because those molecules in the mobile phase are leaving behind their other molecules that have the same properties as them that are on the stationary phase. So you want to have a fast equilibration in and out of the store so that all of you guys kind of stay as a pack. And for that reason, usually having a thinner layer will help, and you might also raise the temperature. That way you don't get too far away. Or of course you can manipulate the flow rate. So to compare open tubular and packed columns again, the open tubular columns have no A term. That A term is 0 because there's no multiple paths, so you get better resolution. Also because there's no packing to resist the flow, you get faster flow rates, and therefore you typically can work with less longitudinal diffusion. The open tubular also lets you have increased sensitivity, so smaller quantities, but smaller quantities of molecule also means lower capacity. So if you have a lot of analyte, you're gonna have to cut it down. And so you just wanna keep your injection narrow, and then once you've put stuff in a nice little thin packet, you're able to continue on and keep your stationary phase thin. That way the C term doesn't get too large with the equilibration time. Now, I've mentioned flow rate a few times. Let's just suppose you have to calculate your flow rate. And so here's an example. We have a packed column. It's for HPLC. The inner diameter is 0.6 centimeters, so these are color-coded. And inside, 80% of that space is filled with stationary phase, and 20% of the space is mobile phase. So the first thing you have to do is calculate the volume of the column. So it's a cylinder, so pi r squared times the length. Diameter of 0.6 means a radius of 0.3 centimeters, so make sure you're doing this in radius. And let's just say it's 1 centimeter long. And so you have 0.283 milliliters of total space when you calculate that out in 1 centimeter of column. And the mobile phase volume is 20% of that. So you have 0.0565 mils in this 1 centimeter, because I just took 20% of the 0.283. The volume flow rate is the milliliters per minute of solvent passing by, and you measure this. You basically put flow through and you get the volume of how much came out in a minute, okay? The linear flow rate is the distance that a solvent is going to travel per unit of time. And so this is centimeters distance down the column per minute. And so you calculate this, and so you're like, well, okay, 0.3 milliliters would occupy how much column length? Because 0.3 milliliters is what came out in a minute. And so you're like, well, 0.3 mils, and now I know from my purple thing there how many milliliters is occupied in a centimeter of this column. So I divide it by that, and I get 5.3 centimeters of column length, all right? So that means that you've got 0.3 milliliters of solvent passing by a point in a minute, and that goes 5.3 centimeters in the column. So those are your two types of flow rates, whether it be milliliters per minute or length per minute. One more thing on the resolution side of things is asymmetric band shapes. So ideally, you have this good symmetrical shape here. And what that means is you have a constant partitioning between the stationary phase and the mobile phase. So there you go, constant. What can happen is you get fronting and you get tailing. So over here on fronting, this will occur when you overload the column. If you put too much analyte on there, some of it doesn't have the opportunity to interact with the stationary phase as it would like to. This is like putting too many people in the mall. They all want to get into the store, but the store is full, and so they just keep walking. And because they just keep walking, they elute early, right? So you're expecting the peak to look like this, but these are all of the things that just come out fast because they don't have any opportunity to interact. Tailing is the opposite. In tailing, some things take longer to come out than they should, so you're expecting it to be down like that, and some linger longer. They're lingering longer because of inhomogeneity in your stationary phase. Some of the sites in the stationary phase are binding to the analyte stronger than others. This can happen over time as your column degrades. And so if you're seeing fronting, you're putting too much analyte on and you should back off in the concentration. In tailing, what that means is you're probably getting some degradation of your column and you might look into purchasing a new column. This slide is overwhelming. This slide is here basically for your reference. You can pause the video and it's got a summary of a lot of the chromatography equations that you might want to have in your notes. Now, gas chromatography. We talked about some basics of gas chromatography, and here I want to talk to you more about resolution and I want to talk to you more about detectors. So the columns in GC we mentioned in class are pretty small. Actually, I think in class I might have said 1 millimeter is the diameter. It's actually less than that. So 1 millimeter is a pretty thick one. So 0.1 to 0.53 millimeter inner diameter is what's shown here. They're really long. They can be as short as 15 meters. They can be as long as 100 meters. And so they're wrapped around this coil. So what you have here is the column is actually there, and that is just a physical support. Open tubular has a few options. With the open tubular, what you're able to have is the larger samples if you have a support coated, and so you're able to have these little beads along the wall. And with the support coated, then you have more surface area, and so you can hold on to higher capacity. But usually it's a wall-coated open tubular, which means just a thin film. The stationary phases, like dissolves like. You've seen this slide before, but I really want you to have it here when we're talking about stationary phase, where you have different things that are bonded to the silica of this fused glass column, capillary column. And so the more you put on things like cyanide groups, the more polar it becomes. Whereas if you have things like methyl groups and benzene rings, then it's more nonpolar. And that kind of depends on how much of the phenyl group you have on there. Can change the polarity a bit. You match your column polarity to your type of analyte. So here are some groupings, things that are particularly polar versus not polar. If you had amino acids or something like that, carboxylic acids, phenols, these are more polar, and you want to use the columns on the previous slide that have those polarities. The thinner your column is, and so we're talking about the inner diameter here, the better the resolution. So side by side, on the left hand here is 0.32 millimeters. Peaks 1 and 2 are not resolved. Peaks 2 and 3 are not resolved, but getting closer. If you can shrink that column, you have a smaller hallway to walk across in the mall, and you're going to have better resolution. But it's a smaller column, and so you can't put as much sample on there. As I mentioned before, the longer the column, the better the resolution, and resolution scales as the square root of length. So if you're doubling that column, and each of these going from 15 to 30 to 60 meters, you're getting the square root of 2 from doubling. And so that longer length gives you better resolution. Now in GC, you've got that stationary phase. And so this is not the diameter of the column. And so a moment ago, I talked about diameter. And so you've got like big diameter versus thin diameter. It's not that. What this is if you had equal diameter ones, it's how thick is the coating. And so you've got that well-coated open tubular, which is like that. Okay? So this is drastically exaggerated, but the coating on the inside. Okay. So thicker coating versus thinner coating on the inside of these GC columns does have an impact. And so if you have the 0.25 micron thick film, which is your thinner version, you don't have as good of a resolution as if you had a thicker film of like 1 micron. And so a nice thick film inside of a skinny column is going to help increase your resolution. However, because you have more of the liquid phase, this bonded liquid stationary phase, it's possible that as you reach higher temperatures, you'll start to lose some of that, and that's called column bleed. So column bleed is when your liquid stationary phase actually starts to come off the column and elute with your sample. All right, choice of carrier gas. Hydrogen, helium, and nitrogen. On the top right, you see those Van Deemter curves, and you know that the diffusion coefficient has a factor in our various terms, right? So you want Good diffusion, but not too fast, right? So here you have flow rate versus plate height. If you want a fast separation, you can really go for hydrogen here. You can really go pretty high, right? So here's our hydrogen optimum, and that's at a linear velocity of like 35, right? So fastest, 35 centimeters per second. For helium in black, we're able to operate at something like, I don't know, 23 centimeters per second. Remember, the faster you go, the more samples you can do at a given point in time. And then nitrogen is like, I don't know, 12 centimeters per second. So nitrogen is not really a very fast method. You're about to learn about some detectors. Nitrogen gives you a really nice detection limit if you're doing a flame ionization detector, and it's pretty common. You can just purify it from air. Helium is like a good compromise. It's really not the best at anything. It's not the fastest. It's not the most sensitive for a detector. It is not the cheapest. It's the most expensive, but it is the most common because it lets you go pretty fast. And it's also not explosive, right? So the hydrogen, which is your super fast option here, if you had a hydrogen leak and you got to greater than 4% hydrogen in the air, you could have explosions. Also, if you're using a mass spectrometer, it's really hard to pump hydrogen gas, and so your pumping for the vacuum in the GCMS isn't very good. And hydrogen is not inert, it's reactive. So it could, saturate your unsaturated organic bonds and change your chemistry. It's fairly cheap. You could electrolytically split water, and so that's cool. But helium is your optimum compromise. It's not your optimum anything, but it's your optimum compromise. As far as the carrier gases go, you can see the influence on resolution. This is the same analytes using the same column, and it's just different speeds that you can go with your flow rate. And so you can see on the left, nitrogen, low flow, nice and slow, crappy, not very good resolution. Helium, yeah, I can work with that. 32 centimeters per second is a lot faster than 10 with nitrogen, but hydrogen is better. When you are putting samples into the GC, you need to make sure that you've got a small plug of sample. It's usually about a microliter, and so you want the sample width here to be nice and small and compact. And it depends on your sample. Maybe you want less, maybe you want more. You're going to be injecting through a rubber septum, which is separating the air in the room from the gases in the column. And that injection port is hot to volatilize the liquid that you're putting in. You want to get a really narrow plug because the thinner the plug of analyte is, the smaller it'll be going through. And you know it's only going to get fatter because of diffusion. So if you have a large plug, big blobby injection, it ain't going to get skinnier. Like, it's big, it's wide, it's not going to diffuse in. That's not the way diffusion works. It's going to diffuse out. So you have to start with a narrow plug. And so you get a little crafty on how you suck up the sample. You make an air sandwich so that you don't want any analyte down here. So the analyte should not be in the needle itself. The analyte should be up in the barrel so that when you push your thumb down and you inject that, that's going on quickly and all at once. The injectors themselves have three different types. From left to right here, we have the split injector. And so what we're seeing on the previous page is the syringe right here. So that's your needle. The blue thing is the rubber septum. And in the split one, what you have is there is some flow going in, right? So like 102 milliliters per minute, for example. Only 1 milliliter per minute of that goes onto the column, and most of it goes to a split vent. So what you're doing is you're wasting part of your sample. 100 out of 102 pieces here is going away. It's actually pretty routine to do this because you want low concentrations on your GC column. And if you have an open tubular column, it's pretty routine to use this. You'll also notice a little bit of it is just going sideways under the septum to purge out any gases that might be leaking through. Splitless is very similar. You still have the septum purge sideways, but basically everything else goes onto the column. So 2 mils per minute of helium carrier gas is coming in, picking up those molecules that you just injected. Hey, there's a molecule flower for you, and then it goes onto the column. On-column injection is got none of this sideways flow rate, and it actually has a physical connection between the needle tip and the column right there. So you're literally putting all of your gas, all of your liquid straight onto the column, and there's no side flow, there's no split flow. And so that's different from this one because here you have this big open void where things are volatile mixing into it and the column is sticking up from the bottom. With split injection, you're going to use this if your analyte makes up greater than 0.1% of your sample. You put the whole microliter of this onto the column. It's going to be way too much. In that split injection, you're able to get some of it to go to waste. And the thing is, though, the split ratio is not very reproducible. The split ratio being how much goes to the vent waste versus how much goes to the column, which is really bad for quantitative analysis. And so hopefully you're using an internal standard. Detection, you need to be able to see the analytes as they come off the column, and there's a lot of ways to do this. Physical properties, things like the emission and absorption of light, temperature, mass spectrometry. You're going to integrate the peak areas. No matter how you use it to detect it, you're going to get that peak area, and you're going to use the internal standards, which you should recognize that internal standards equation there. And so our options for detectors for GC, you really should study this table. I'm going to tell you about a few of them. So what's listed here is the detector. The detection limits, that's how low you can go, right? Remember, detection limit is 3 times bigger than the noise of a blank. Linear range is how many orders of magnitude you can keep a nice linear line. So there's my linear line. 10 to the 5th, right, is 5 orders of magnitude. So 5 powers of 10. And so we can see here, like, first of all, it's different units, which is kind of annoying, like femtograms per second for nitrogen and phosphorus versus picograms. But smaller numbers are better for detection limit, and larger linear ranges are better. So most common ones. Okay, your thermal conductivity detector is simple, it's universal, it responds to nearly every analyte. The idea is that you have a tungsten filament, and so you can see in the middle of these 2 diagrams the hot filament. And what's shown here side by side is 2 options. You have low volume for an open tubular, and so that's this one, open tubular. And there's also a higher volume one where you've got like a packed column. But both of them are working under the same principle. The principle is that your eluent flows in, it flows past that hot filament, and it flows out. Your carrier gas will have a different thermal conductivity than your analyte. Hydrogen and helium in particular have high thermal conductivity, and so they'll dissipate the heat from that hot filament more easily. When your analyte comes through, it elutes, it's going to decrease the thermal conductivity. Now, if it's got decreased thermal conductivity, the filament will get hotter. It turns out that the filament's electrical resistance goes up when it gets hotter. And because current is related to voltage using resistance, you get the voltage across the filament changing, and that means detection. It is really good for packed columns. It's more sensitive at lower flow rates because you're going slower and you're able to get this change in temperature more easily. It's still possible with open tubular columns, but it's less sensitive than other detectors. But like I said, universal, works for all molecules. The flame ionization detector is not universal. What it is you have a flame, right? So here's our flame right there, and you're burning the analyte. So it's used for hydrocarbons. And if you are burning a hydrocarbon, 1 in about 10 to the 5th, so it's not many of them, but some of them will produce an ion from burning. And so you have some kind of hydrocarbon plus oxygen, and you're getting a CHO plus and an electron. It'll measure the current from those electrons and from those ions. That's the whole flame ionization detector. Flames cause ions. You've got some electrodes, right? So there's a negative electrode and a positive electrode, and the current between them is measured. It's not sensitive to non-hydrocarbons. If you're using this, nitrogen will give you the best detection limit. You'll get to the lowest concentration, and the signal it gives is proportional to the number of susceptible carbon atoms. You do need standards to figure out what concentration relates to what peak area. But you get 100 times better detection limit than thermal conductivity, and you get a really high linear response range. So a lot of people analyze hydrocarbons, and this is a very popular detector for that purpose. For things that contain electronegative species. You have the electron capture detector. We used to have this, and then we got rid of it. And when we got rid of it, we had to get rid of the radioactive source. Super fun getting rid of radioactive material. So you have a nickel radioactive source here. And what that radioactive source is doing is it's releasing high energy electrons. Okay, those high energy electrons go in, they ionize the gas that's flowing through. And analytes that have a high electronegativity, a high electron affinity, capture some of the electrons and they decrease the conductivity of that plasma. So like this is plasma of ionized gases and electrons, and here comes your analyte, right? You've got gas in, gas out going there. And so if it takes some of those electrons, you no longer have such a great number of charge carriers, you no longer have such a great conductivity. It's not sensitive to hydrocarbons, it's not sensitive to alcohols, it's not sensitive to ketones. These are not electronegative enough. But things that contain halogens, conjugated carbonyls, nitriles, you know, the top list over here, particularly the halogens, are really good with the electron capture detector. Some other ones, so we just talked about electron capture, we just talked about flame ionization detection. The other things that are very specific, nitrogen phosphorus, as the name would tell you, does nitrogen and phosphorus. You can use a spectroscopy, particularly chemiluminescence works for sulfur and nitrogen. And then also there's mass spectrometry, which is useful for most analytes. So in the comparison of these different detectors, here's a sample of natural gas. And what you see is that on the top, you have the flame ionization detector, and you're getting peaks every time you get one of the hydrocarbons eluting. And so methane, ethane, propane, etc. And some of these have branching, right? So you've got isopentane versus N-pentane. And that long linear one has more spread and therefore can glom on to the stationary phase and stay there longer. But if you switch to a sulfur chemiluminescence detector on the bottom, it's only going to show these organosulfur compounds, and they're too dilute, right, to see with the FID. And also some of them don't even have hydrocarbons in there. So the ones that are like too dilute, like this, it's partially hydrocarbon, but it's low concentration. So you need this really sensitive sulfur chemiluminescence detector to see it. Others, like SO2, simply are not hydrocarbons, and so are never going to show up on the FID. Furthermore, the sulfur chemiluminescence is only going to detect things that have sulfur. So it really lets you put on a different pair of glasses to see different aspects of your sample. Now, I mentioned mass spectrometry a moment ago. The analytes here are ionized by something called electron ionization. So you have electrons coming off the filament. Those electrons hit your sample, your gas that's coming off the column, and ionize your sample. Your sample makes positive ions. Those ions are then separated by mass, so they're accelerated and separated in space. So it's like time of flight mass spectrometry, or maybe you're using a magnetic field to separate them out. And the chromatograms are specific to elements, molecules, or molecular fragments. So when you're using these specific things, you can do what's called selected ion monitoring. So up here, our reconstructed total ion chromatogram. This is everything. So total ion chromatogram is also termed TIC. If you're doing the GCMS lab, you will have seen TIC. But if you choose to pick, say, the peak at 78, that is going to be very particular to benzene and to things that have benzene cores, like ethylbenzene and xylene. And so it's really helpful for you to be able to select a particular ion, and you can also use the mass spectrum to identify your samples and to confirm what you think the peak is. Another thing is that you can also look for what's called ICP-MS. So you have gas chromatography, in this case, to separate the pesticides. You burn them in a plasma, inductively coupled plasma, to ionize and fragment the molecules, and then you do mass spectrometry to identify them. And so you can see with these different traces here, you're seeing like phosphorus if you have something with a phosphorus in it, you're seeing sulfur if you have sulfur, and so on and so forth. Okay, details on HPLC that we haven't gotten to. All right, HPLC. What you have is you always have to put your sample in. So you have either an auto sampler or a manual injector. That will go, and you've got pumps that are pumping the liquid through, and your column is a short metallic column, short compared to GC. And what will occur here is that it has to go to some kind of detector. We'll talk about the detectors. Sometimes you will have an oven that's controlling the temperature of this column. And don't forget that it's always wise to have a guard column in case you have particulates that could clog up or destroy your analytical column. The injection for HPLC, whether it's an auto sampler or it's manual, will usually operate using the 6-port injection loop. So it has 2 positions. The left-hand side here is showing the load position, and the right-hand side is showing the injection position. So we've got my molecule on the top here. My molecule is this cute little round ball. And in the load position, what we're trying to do is we're trying to fill this sample loop. So the sample loop is this part. We're trying to fill that with your sample. And so it goes in and it goes around and fills that loop, and then some of it continues out to waste. So you have that loop entirely filled, maybe even overfilled, so that you got the whole thing. Now to inject, what will occur is that you turn this valve and it's going to change the positions. So if you look carefully from left to right, you still have that same loop, but now what's going to occur is that you have your mobile phase coming in from the injection position, and that now is set up to go through your sample loop. And so it's going to come through mobile phase and push that volume onto the column. So the injection volume in this case is determined by the size, the volume of that injection loop. For detection in HPLC, you have a lot of options. One of those is spectrophotometry, which we love so much because it's super useful. Usually you're looking at absorbance in the UV, but you can pick a wavelength, so you can have a whole spectrometer as your detector, and you might wonder about the cuvette, because you have stuff flowing off a column, you have liquid stuff flowing off a column. How are we going to get this into a cuvette and do it in real time rapidly enough? And the clever way that they came up with this is to actually have the path of the liquid bend and then go on out. So this distance here from end to end across the bend, you've got little windows, and so you can pass the light through from left to right across that particular length of the capillary. And that length is your path length for the spectroscopy and allows you to get enough detection. So detectors for HPLC certainly include that ultraviolet, which lets you get a nanogram of detection limit. You also have mass spectrometry, so that's the other star. These are the 2 that we have at Niagara, and it gives you about the same detection limit, 0.1 to 1 nanograms. You'll see that there are other options here. Fluorescence, for example, is going to give you lower detection limit. We know that fluorescence is more sensitive if it works with your molecule. But the other thing to notice in this table is whether something is useful with a gradient. Gradient elution really helps you to save time and get better resolution. But some of these things, like refractive index, are really not useful with a gradient because they depend on the property of the solvent. And so if you're changing the solvent with those, then you've got problems. But ultraviolet and mass spec don't have any issues with gradients. You can move forward with your life happily doing that with gradients. The stationary phase in HPLC. First of all, HPLC is high performance liquid chromatography. Sometimes people accidentally, incorrectly call it high pressure, although you do have high pressures. Almost all HPLC columns are packed. The solutes diffuse too slowly in liquids in order to really use an open tubular column practically. This packing, if you have smaller packing particles, you get better resolution. So we're always worried about better resolution. And I'm always interested in making sure you know, winky face, what makes better resolution. So smaller particles do that. But the other thing is that a smaller particle is going to resist the pressure more, and so you're going to require a higher liquid pressure with those smaller particles. But that's not insurmountable. We can totally handle higher pressure. All right. So the column packing is made of silica. You either have what's called monolithic, which means it's all one ceramic going through the whole cylinder, and it has micropores, and you can see using the SEM images here that you have a scale bar of about 5 microns here, and so you have about 5 micron pore size in that particular one. Or you can have single particles where the whole thing, for example, is 4.4 microns across, and then it has porosity within that. This has really high surface area, a lot of opportunity for your analyte to interact with it, but it is solid and it does have pores. Now, the particles don't have to be completely porous. You could have a solid core to your particle, and then you could be superficially porous, and so you can see that in the blue here. They really are pretty nice. They act smaller than they are, and so that means you get the separation of small particles, but you have the lower pressure of a big particle. The small particle size will decrease that plate height and improve the resolution. So here's our Van Deemter equation. If you have small particles, what this does is it means you have fewer options in the multiple paths term. And so what we see here is going down this list, you get better with those 1.8 micron pore size, for example. The other thing is that the diffusion length for the equilibration is about the same order of the particle size. And so we don't want a really big diffusion length because your friends are going to move past you when you're still in the store, right? So it's the C term. And so that blue one, the 2.7 micron fused core superficially porous thing, is what I was just talking about, where you have a solid core. It's actually a physically bigger particle, but the surface of it is smaller particles. And it really can act like a much smaller particle. Plate height and pressure both will change with particle size. So what you see here is our particle size decreasing from 5 microns to 1 micron. Again, this is packed HPLC. And what we see is the plate number. Remember, high plate number is good. The more plates you have, the better resolution. But you also see that the pressure required to push through that is considerably higher. But it's coming out a lot faster, right? So small particles, faster tension time. Good resolution, high plate number, but higher pressure, which means more instrumental requirements, more money. Okay, how do we get chemistry onto these particles? So I talked about mesoporous silica or silica beads. Silica is glass or sand, and its surface has all of these beautiful silanol groups, so SiOH. These free OH groups can strongly bond to polar solutes. Remember, having a very strong bond means that the analyte isn't going to release, and you can get tailing. Things will bond really strongly and come out late, and you'll have poor peak shape, which can cause poor resolution. So what we do is we put chemistry on top of this. If we put chemistry on top of it, we can do a few things. The first thing that we can do is change the fact that bases, like OH, right, will dissolve silica. And so at pH greater than 8, just bare silica columns are going to dissolve away, which is bad. If you put this ethylene bridge, which is in red here, across things, then you're able to make this resist basic conditions and be tolerant up to pH 12. So we're fixing stuff with chemistry. The other thing you can do is you can bond things to the silica. So now you have the silica surface here, and you're putting on a organochlorosilane, and that chlorine is going to pop off and react with the OH, right? So this little guy and that little guy are going to react with each other, and ultimately you're going to get an SiO-Si bond, and now you've got R groups on there, and R groups are magic. This lets you change the polarity of things. So your common R groups down here for polar, things like amino, cyano, diols, stuff like that. Nonpolar is long hydrocarbon chains. That lets us get into our famous C18 with 18 carbons and C8 with 8 carbons, and that's lovely. The other thing is that you can have multipole chlorines. Multipole was said we were there, right? Multiple chlorines there let you double bond across a couple of O groups, and these are also more stable and will resist bleed more. So C18 stationary phase then has a silica bead with the silicon, oxygen, silicon to the carbonate chain. And like I mentioned, the double bonding to that stationary phase helps. You can also cross-link, and so you can add that cross-linker there to stabilize your stationary phase and prevent column bleed. Column bleed being the loss of the C18 over time. The elution basically dissolves in your mobile phase and goes away, which sucks for you. Okay, so common stationary phase choices. If you have a nonpolar C18, C8, and C4, it's van der Waals. If you have hydrophobic, aka nonpolar compounds, then the C18 is going to retain them more strongly. Phenyl is also nonpolar, so phenyl is that benzene ring friend of yours. Basically does the same thing, except it includes pi-pi interactions with the double bonds. Cyano is considered intermediate polarity, and that's pretty nice. Amino and bare silica are more polar, and bare silica is very, very polar, interacts with things through hydrogen bonding, and is definitely a normal phase separation. So see over there, reverse phase, normal phase, kind of deal. All right, HPLC method development. I have 3 more slides. You have 3 more minutes, right? So this isn't too bad as far as a lecture goes, only 55 minutes instead of 3 hours of the other videos. HPLC is really easy to use once you have a method. Getting a method can be harder. So I just want to talk to you about method development for HPLC. You're trying to get good resolution between all of your analytes in the least amount of time possible. Talk to you in class about adding gradients, and that's certainly part of this. When you're developing your method, you have to first change the things that are easy to change, and changing your solvent strength by changing the fraction of each solvent, going to a higher eluent strength or weaker eluent strength just by changing the percent of solvent A and solvent B is really a good way to go. You can also change the temperature. If you have a column oven, the higher temperatures will decrease viscosity and help with resolution sometimes. You can change the pH in small steps because remember that the pH will change the ionization or non-ionization of particular analytes. You can entirely change your solvents, not just the ratio between aqueous, buffer, and methanol. You could change out from methanol to acetonitrile, for example. And the things that are harder to change are using the stationary phase because you have to buy a different column. You have to physically purchase, and these things run several $100s, a different chemistry column. But it's possible to change that. Try the other stuff first. Your starting conditions for a reversed phase are summarized here. So if you ever need someplace to go to start, gives you your kind of normal milliliters per minute and your normal size. And you see here that with a C18 column, it's typical to go 1 milliliter per minute. And in here, your neutral analytes will typically have CH3CN, which is acetonitrile, and water. And you're usually going 30 to 40 degrees C, and you're probably putting about 5 to 10 microliters on there if you're doing a 0.46 centimeter column. And this basically is a good starting point. I'm not going to read everything to you. Once you have a starting point, then you can usually achieve the best separation with a mixture of solvents. Maybe you want 3 solvents, in which case you can do this so-called method development triangle, which means that you test your sample with each of the 3 pure solvents. So the pure solvents being, say, acetonitrile, methanol, and THF. And then you're going to go halfway between each of them, right? And that'll give you these 3 positions. And then you can do a 33, 33, 33 mixture. And once you do all of these, you're going to characterize the resolution, do that Van Deemter equation if you want to with flow rates, but really look at the resolution that you're getting here, and that'll help you decide. So that's it. Good luck on your quiz. I'll see you later.